Swayam Prabha. Digital India. Educated India.
We have come to the last lecture of week 3. Let us have some more discussion on shocks and expansions in this lecture. To begin with, we will revisit the effect of degree of freedom of the gas on the thermodynamic properties by considering a normal shock, which we already initiated in the previous lecture, and in this lecture we will just recapitulate a bit of that once more. Then we will move on to shock and expansion wave relations when we apply them to flow past a thin flat plate. And finally, we would compare the results of shock expansion theory with the Newtonian theory, which we learned in the context of hypersonic flow. So, this topic we had already had an initial look in the previous lecture. Let us relook at some of the details. We see that gamma, which is the ratio of Cp and Cv, the specific heat ratio, can be expressed in terms of the degrees of freedom of the gas. And by now we understand that as the temperature of the gas increases, different modes of energy get excited, starting from the lower temperatures to the higher temperatures, beginning with translational mode, followed by rotational, subsequently vibrational, and at much higher temperatures electronic energy modes get excited. And as they get excited, we understand that the behavior of the gas changes from a calorically perfect one to a thermally perfect one, followed by real gas effects or high temperature effects, which occur when we have a reacting gas. Calorically perfect gas, of course, we recall that Cp, Cv, gamma are all constants, while in a thermally perfect gas they are functions of temperature. When we look at the details, when we discuss statistical thermodynamics or microscopic thermodynamics, we would be able to deal with these things in further detail. Here we see a plot, a schematic which shows how gamma would change as the degrees of freedom increase. As you can understand, as different energy modes get excited, we expect that the degrees of freedom that the gas attains keeps increasing. And there seems to be a fall in the gamma value as more and more energy modes get excited. We know that for air at standard temperature and pressure, we consider gamma to be 1.4, which is somewhere here or here perhaps. On the left side, the plot indicates the variation of the pressure ratio P2 by P1 across a normal shock. And on the right hand side, you see the P2 by P1 ratio as the degrees of freedom increase, and also the Mach number of the upstream flow changes. So, these two are kind of comparative plots which show you the effect of change of gamma. As you can see that there is a monotonic increase in the P2 by P1 ratio, and if we consider a calorically perfect gas, by the time the upstream Mach number reaches a value of 10, the P2 by P1 goes well beyond 100. There is A similar variation when we consider the variation of n, there may be minor differences which is not exactly visible in this plot, but we get to see a nice contour plot which covers a range of upstream Mach numbers and different degrees of freedom. So, that we see a carpet of values for P 2 by P 1. The effect becomes a little more visible when we consider the density ratio. As m 1 tends to infinity, you might recall in one of our earlier lectures we had shown through a limiting exercise that the density ratio will tend to a value of 6. If we consider that even at much larger values of upstream Mach number, the gamma would still remain constant. So, that is what it will saturate to as the upstream Mach number becomes really high. However, you find that in the case of a gas where the n value is variable, which means consequently the gamma is also changing, and in some sense we are taking into effect the temperature in this modeling. The rho 2 by rho 1 seems to be going well beyond 6. At larger values of n and m 1, it seems to be going even beyond 7. That is an interesting feature to observe. The feature becomes even more interesting when it comes to temperature ratio. To derive the temperature ratio, of course, from the equation of state we can make use of the pressure ratio and the density ratio and multiply them together. For a calorically perfect gas, you see that for upstream Mach number of around 10, the temperature ratio can go beyond 20, while interestingly the temperature ratio falls in the case of a changing gamma situation for large values of n and fairly high values of upstream Mach number. So, here not that we will be able to discuss about these aspects in much detail before we actually undergo more detailing on the thermodynamics aspects from statistical or microscopic point of view, but still one comment may be made that as we approach higher Mach numbers and more energy modes get excited, the energy content of the gas will essentially get distributed over different energy modes, and the temperature that we see over here is essentially reflecting the energy content that we have in the translational mode. So, for the same total energy, less amount of energy on a comparative scale will be available for the translational mode if large number of degrees of freedom have been excited. Consequently, there would be a drop in the temperature ratio which is manifested here, because that basically is manifesting the translational energy mode contribution only. As far as the downstream Mach number is concerned, again you see that it falls down dramatically as Mach number becomes large. So, this is the gamma equal to 1.44 case, the calorically perfect one, while here again you see a carpet of values which do not show much difference, of course, compared to the values that we see here for the calorically perfect case. And one thing that would be interesting for you would be to try out writing a small code which can do these calculations much more conveniently. So, here we are showing an example Python code, and you notice that in the code we have defined the degrees of freedom varying from 1 to 7, and again the Mach number varying from 1 to 10, and then you perform the different calculations for pressure ratio, density ratio, temperature ratio, ratio of sonic speeds across the shock wave, and Mach number ratio, etc. So, this is really interesting to pursue, and I would encourage you strongly to try out writing a small code. You can choose any language that you wish, and then you need to use a suitable post processing tool to display the results in a way similar to what you saw in the previous few slides. So, with that we move on to the last section of this week's lecture content. We would like to revisit the Newtonian flow model, which we said works very well for hypersonic situations or hypervelocity situations. And we would like to compare the case with a slightly lower Mach number range, where we use the shock expansion theory applications usually, and then try to compare the result of the shock expansion theory with that of the Newtonian flow and get a kind of comparative picture on the same. Here you see a thin flat plate which is kept at an angle of attack of about 5 degrees facing a free stream flow, which is of course uniform, and you can have different Mach numbers with which the flow approaches this flat plate. If you assume that the Mach number is much larger than 1, then Newtonian theory of course gives us reasonably good predictions, that is known from literature, and the Newtonian theory result for the Cp distribution on the windward side of the plate is given by 2 sin square theta, which comes out to be 0.015, and we say that the leeward side would have a Cp value of 0, because the leeward side is not under the influence of the directional motion of the moving particles. It sees only the effect of random motion of molecules, and in the Newtonian theory random motion of molecules will of course not have any significance in the Cp calculation, and therefore pressure on the leeward side in terms of the Cp will go to 0, which basically means that you have a Cp value of 0.015 acting on the lower surface or the windward surface, and a value of 0 acting on top. And based on the Cp distribution, if you resolve them parallel to and along the direction of the flow, you would end up getting a lift and a drag value, and from where you can compute the Cl and Cd acting on this flat plate. If we were to consider the actual flow field features which are visible at lower Mach numbers, then we would see an expansion fan here, we would see an oblique shock here, and then M1 is expected to be of a much lower order of course, and because of the oblique shock in the lower side there would be a compression of the flow, and therefore a higher Cp expected to be acting on the windward side, a comparatively lower Cp acting on the leeward side because of the expansion of the flow through the Prandtl-Meyer expansion fan. So, these two are the major flow features that we can see over here due to the compression and the expansion respectively. Now, if we proceed with the calculations, let us take two cases, we will call them, let us say case A to begin with, where we assume an upstream Mach number of 3, and later on you will see we will take up a case B where the upstream Mach number will be much larger, typically representing a hypersonic or hypervelocity flow. This is typically low to moderate supersonic Mach number range that we are talking about. If you look at the Prandtl-Meyer expansion which occurs on the upper surface, you can calculate the nu 2 after the expansion occurs, where the expansion angle, if you call it theta, that would be 5 degrees because of the inclination of the plate, and the upstream Mach number before the flow undergoes the expansion is 3, based on which the nu 1 can be read from the Prandtl-Meyer function tables. It is found to be 49.76 degrees. Therefore, if you add 5 degrees to that, you would end up getting the value of the function downstream of the expansion fan. Now, if you read the Prandtl-Meyer expansion tables, let us go to the table and we will come back again. You would notice that for an upstream Mach number, for a Mach number, local Mach number of 3.25, which you find over here, the nu 2 is found to be 54.35 degree, and again the local Mach number of 3.3, you will get a value of 55.22. So, these are the relevant values for us, and we just had a look at the portion of the Prandtl-Meyer function and Mach angle table. This is the Mach angle, this is the function value. We will go back to the calculations where we left and we will plug in these values which we read from the table, and then we notice that the actual value lies somewhere in between. The actual value happens to be 54.76, which of course is lying in between, and we basically assume a linear behavior within this interval, and therefore, we interpolate the value. So, we know the new value at that Mach number. Based on that, we interpolate the actual Mach number based on the range of values that we are talking about over here, and we find that the interpolated Mach number comes out to be 3.27, which of course lies in between these two values. Now, for that particular Mach number, we would be interested to know what would be the ratio of P naught 2 by P 2, and for that you of course have to read the isentropic flow property tables, because through the Prandtl-Meyer expansion the flow is undergoing an isentropic expansion. We have a portion of the isentropic flow table here. So, if you read the tables, you find that for Mach number 3 you get a P naught by P of 36.73, which we have recorded here, and you have values which are close to 3.7, a little less than that and a little more than that, which are found here 53.2 and 57.22. Again, based on a linear interpolation, you can actually get the value of the P naught 2 by P 2, which is the stagnation pressure ratio downstream of the expansion fan, corresponding to the Mach number downstream of the expansion fan of 3.27. So, we have the relevant values of the stagnation pressures, and we note that across the Prandtl-Meyer expansion the flow remains isentropic, and therefore, the stagnation pressure remains conserved. Now, if you take the ratio of these two terms in a manner that you can get the ratio of the static pressures, then these are the two numbers which are important for you. You get a value of 0.67. So, there is a reduction of the static pressure after the expansion, which is of course what is expected. So, this is basically the end of the expansion fan calculations for the case A. Now, we need to look at the lower surface where you have an upstream Mach number of 3, the flow undergoes a compression of 5 degree, and you can refer to the theta beta m plot and obtain the value of beta, which will be around 23 degrees. Let us move to that plot and see whether we can figure it out. So, we have taken the theta beta m plot in a slightly unconventional way. We have turned it by 90 degrees in a counterclockwise direction, where the beta now orients in this direction and the theta orients in this direction. And if you read the plots here, you will find that different values of Mach numbers are recorded here. So, for example, this is the one that we need for our purpose, and accordingly you have to read the value corresponding to the compression angle. So, you have a compression of 4 degrees here, and between 4 and 8 you have 8 divisions, and therefore, the 5° angle basically comes here. Now, if you move up, remembering that this is the one that you have to follow. So, this is the plot you are actually following down, and then you try to move up from the 5° angle. You will find that the intersection occurs at around 23 degrees or so, and then from there we are able to figure out that beta will be around 23 degrees. Based on that, you can calculate the normal component of the Mach number upstream of the shock, or rather downstream of the shock. Yeah, I think this is upstream of the shock. It is correctly represented as state 1, and that comes out to be 1.17. And now we want to have things downstream of the shock. So, with this we want to find out what is the value of P3 by P1, that is basically going to be obtained from the normal shock tables. So, if you have a normal component of Mach number of 1.17, then it lies between this precisely midway, and therefore, you can just take an arithmetic average of these two values, which we have done over here, to obtain the P3 by P1 value corresponding to that upstream Mach number and beta. So, we look at the calculations once again over here to understand the implication, and therefore, the pressure ratio comes out, and therefore, you should be able to get the P3 now just behind the shock. Now, we have generated all the information which is required in order to calculate the lift and drag forces which are acting on the flat plate on a per unit span basis. So, when we put a dash on the lift or drag, we assume that we are taking unit span, and therefore, the area works out to be C into 1. This of course, is the effect of the angle. This is the effect of the pressure acting on the flat plate as a difference between the lower and upper sides. The flow is of course inviscid, and the normal component of the force, it would act on the plate due to the pressure difference. The normal force can be resolved into lift and drag forces, and the drag that acts in this case is of course not having its connection with skin friction drag or shear stress related drag. It is what we call as wave drag, which occurs in compressible flows. So, we got the pressure difference resolved into two directions now and converted into forces by taking into account the area. We additionally need the free stream dynamic pressure, which is expressed in terms of gamma by 2 P1 m1 square. This of course, we have already discussed, that is the projected area, and from there the lift coefficient can be expressed like this, L dash by Q1 times S. It comes to an expression like this, and then if you just plug in the values which you have computed, you get a value of 0.12. Similarly, you can work out the drag coefficient, it comes out to be 0.01. So, we are done with the calculations for case A. We will consider case B with a much higher upstream Mach number. As a consequence, you will find that the Prandtl-Meyer function value changes, it becomes 102.3 degrees. You add 5 degrees to generate the value of nu 2, which is downstream of the fan. Read up the Prandtl-Meyer function tables to obtain values for Mach number 12 and 13, which lie below and above this angle. Carry out a linear interpolation to arrive at the interpolated value of Mach number downstream of the expansion fan, which happens to be 12.22. So, the flow has accelerated across the expansion fan. Now, we go to the isentropic flow property tables, and we can read the tables to obtain the values of the stagnation pressure to static pressure ratio for upstream Mach number 10 and downstream Mach number of 12.22, and we end up getting the static pressures here in the denominators, which we would ultimately need. When we take a ratio of those two values, we end up getting the static pressure ratio, because the stagnation pressure ratios are conserved across the expansion fan. The static pressure ratio comes out to be this. These values, you will find that if you are to do the calculations using exact closed form relations, they will be more accurate than these ones, which are coming from the tables, which are slightly approximated, because approximations become inevitable when the numbers are coming out to be extremely large, because they are expressed in the index form. So, you can try repeating these calculations yourself with the exact forms, and you will find some differences. For the lower surface, again you carry out the calculations of the oblique shock. You first find out the wave angle. You notice that the wave angle has become much lower. In the earlier case, it was 23 degrees, now it has reduced to 9.5 degrees, which means that the shock is getting very close to the body, and which also means that the Newtonian flow model is fitting in better into this kind of a flow field. The normal component of the upstream Mach number is 1.65, and based on the normal shock tables and with some suitable interpolation, you get the value of P 3 by P 1. You plug in the values of P 3 by P 1, P 2 by P 1 that you have obtained in order to get the CL and also the CD. So, this procedure is of course very similar to what we did for the lower Mach number, but here we are repeating it for Mach number 10. Returning to the Newtonian flow result, this is something that we had already worked out earlier, but now we are going to resolve that into two force components CL and CD, first by obtaining the normal force component based on the pressure difference. So, the pressure difference between the upper and lower surface, that is integrated over the length of the plate in order to get the normal force coefficient, that comes out to be 0.015, and then we resolve based on cos alpha and sin alpha, we get the CL and CD values. This of course is a cartoon of the Newtonian flow model, which we recall, and now comes an interesting comparison of the values. So, at Mach number 3, the CL and CD using the Newtonian flow results, of course, which has no connection with the Mach number, it is independent of Mach number. It gives you values of this order 0.015 and 0.001 for CL and CD respectively, giving you a CL by CD ratio of 15, which is purely based on the alpha or theta of the plate, and therefore, the Mach number is relevant only when you look at the shock expansion wave theory. So, for that Mach number and 5 degree angle of attack of the flat plate, we see that CL comes out to be 0.12, CD to be 0.01, and the CL by CD ratio coming out to be 12. So, though we do not match very well on CL and CD, which is also expected because this is a much lower supersonic Mach number, the CL by CD is not very different from what the Newtonian theory predicts. The wave angle happens to be 23 degrees here. When we go to Mach 10, wave angle becomes 9.5, which as explained earlier looks closer to the Newtonian theory model, where we have a real thin shock layer, and in the Newtonian theory we assume that that shock layer is vanishingly small or does not exist at all. The CL comes out to be of this order, the CD here, and CL by CD interestingly is approaching the Newtonian theory more closely than what you have at Mach number 3. Perhaps if you repeat this at a still higher Mach number, you are expected to get CL by CD ratios which are closer to the Newtonian theory. Let us conclude by saying that we completed the discussion on effect of degree of freedom of the gas on thermodynamic properties across a normal shock. The results were generated using a Python program, and you are encouraged to develop a program of your own. We recapitulated the shock and expansion relations through a numerical problem to solve flow past a flat plate, and we chose two different Mach numbers 3 and 10. The lift and drag coefficients were obtained and compared with the Newtonian theory model. It was found that the shock expansion based calculations yielded closer values to the Newtonian flow model when we consider Mach number 10, which is typically a hypervelocity or hypersonic kind of Mach number, because of strong expansion in the leeward side leading to low pressure and smaller shock angle on windward side leading to a flow which resembled more closely with that of Newtonian flow model. So, the numbers or the outcomes were such that we were convinced that they are working in the direction that we expected them to. Thank you.